14 degrees Fahrenheit minus 10 degrees Celsius. That's the number. Below that temperature, paraffin wax in diesel fuel starts crystallizing. The engine isn't frozen yet, and the clock has started. Cold weather does not kill locomotives by freezing them. It kills them by making them burn. Every disaster on this list started the same way, not with snow or ice, but with oil too thick to move. If 14 degrees does this to fuel, what does minus 28 degrees Celsius do to 112 loaded grain cars parked on the steepest grade in North America? In the 10th place, the lubricant chain marks where the cold first asserts control. As temperatures fall below minus 20 degrees Celsius, locomotive oil thickens from a flowing liquid into something closer to syrup. The numbers are unforgiving. Viscosity jumps to 800, even 1200 centistokes, 4 to 6 times the safe design value. The thin film that should keep steel from grinding on steel shrinks below 1 micron, until the bearing surfaces are separated by less than the width of a red blood cell. Within 3 minutes, the transient elastohydrodynamic model predicts the film will collapse entirely. Once that happens, friction and heat begin to climb in a runaway loop. Thermal imaging from Anton Parr's lab confirms the sequence. A bearing surface at minus 30 degrees flashes to over 120 degrees in under a minute. The hotbox detector, if it is close enough, might catch the spike. But when the oil fails, the clock is already running. A delta T of 90 degrees Fahrenheit is all it takes to cross into damaged territory. The cold does not freeze the train in place. It quietly strips away the last layer of protection, leaving metal to destroy itself from the inside out. This is the first link in the failure chain and the foundation for every disaster that follows. Number 9, the fuel chain is where the cold asserts its second, more insidious grip. Diesel number 2, the lifeblood of every locomotive, carries a silent limit. Its cloud point hovers near 14 degrees Fahrenheit. Below that, wax crystals begin to appear, first as a haze, then as a dense network that chokes the fuel filter. Laboratory tests, codified in ASTM cold filter plugging point protocols, show that even the best anti-gel additives can only push this threshold down by 20, maybe 25 degrees before the chemistry fails. The so-called Arctic limit is not a guarantee, it is a line in the sand. Operators are told to dose at 0.2%, to stir for half an hour, to let the tank settle for a day. But in the field, as in Minnesota in 2022, a 5-minute mix left pockets of untreated diesel, some at 0.05%, some at 0.25%. The result was a cold filter plugging point 12 degrees above target, and a locomotive stranded at minus 28. When the wax hits the filter, fuel flow collapses, combustion pressure drops, and the engine starves. The bearings, already fighting thickened oil, are now loaded harder at lower RPM, accelerating the slide towards seizure. The cold does not just slow the train, it strips away the margin for error, one subsystem at a time. 8th place, the brake chain. Marks the moment when the last engineered safety margin begins to bleed away. In sub-zero darkness, the air brake system is governed by seals made of nitrile butadiene rubber, chosen for flexibility but only above minus 5 degrees Celsius. Below that, the polymer hardens, losing its ability to conform and hold pressure. Laboratory tests show a relentless pattern. At minus 28 degrees Celsius, each 10 pounds per square inch of stored pressure leaks away at a rate of 0.03 pounds per square inch per minute. For a train parked on a steep grade, this means that after just 3 hours, enough air has bled off to erase the engineer's only reserve against gravity. The physics is silent, but the outcome is loud. The brakes that once held a 100-car consist on Field Hill become ornamental, while the train's mass begins to move under its own weight. Canadian National's operating manuals warned of this, and yet procedures allowed trains to idle on grades through the night, trusting seals that the cold had already claimed. The brake chain is not a single failure, but a slow, cumulative surrender, one that turns fuel and oil problems into runaway risk and leaves the final decision to gravity. Number 7. Field Hill, where the pattern of mechanical failure gives way to the slow violence of institutional neglect. On this stretch of Canadian Pacific track, the grade is unforgiving, 2.2%, dropping into the Kicking Horse River Valley, with winter lows that routinely breach -25 degrees Celsius. For over 40 years, Field Hill was a known quantity. More than 25 documented runaways between 1976 and 2018, each one a warning. Each one entered in the Transport Safety Board's ledgers. The response was simple, rational, and written in the operating manual. A temperature restriction. No train would descend Field Hill if the forecast called for -25 degrees Celsius or colder. This was not a suggestion. It was a hard stop, a recognition that the cold strips away every engineered margin. But in December 2018, an internal memo swept the rule away. The language was clinical: operational flexibility, improved winterization, cost savings. The voices of field engineers, the weight of incident logs, the lived memory of crews who had watched brake pressure bleed away in the dark, all of it was set aside. 6 weeks later, the cold returned, and with it, the same physics. Seals hardened, air bled off, and a train sat helpless on the grade, waiting for gravity to finish the job. The Field Hill restriction was not just a policy, it was the last institutional barrier between risk and routine. Its removal did not invent disaster, but it made catastrophe inevitable. The record is unambiguous. The cold did not change, only the willingness to treat it as a limit did. Number 6. The hot box paradox, where technology and policy collide in the cold. The sealed bearing mandate of 1963 was meant to end the era of catastrophic bearing failures, but the physics never left the stage. As temperatures fall and oil thickens, a bearing can go from normal to thermal runaway in under 5 minutes. The only line of defense is the hotbox detector, its sensor, its spacing, and its alarm threshold. The industry standard, set by the Association of American Railroads, places detectors every 10 miles, promising a 99% chance of catching a failure before disaster. But the numbers tell a harder story. Moving to 5-mile spacing would push detection to 99.5%, but at a cost of $12 million a year. The threshold for a critical alarm sits at 115 degrees above ambient, a number chosen for statistical efficiency, not for the physics of a bearing on the edge of seizure. In East Palestine, those extra miles and those extra degrees meant the warning arrived only after the bearing had already crossed into the zone of irreversible damage. The detectors worked as designed. It was the design that failed. The paradox is not a lack of technology, but a surplus of compromise. Economics set the intervals, policy set the thresholds, and the cold simply waited for its cue. The result is a system that can catch slow failures, but misses the rapid ones that matter most. The cold did not invent this gap. It revealed it, mile by mile, reading by reading. Number 5. The 861 accidents nobody counted, where the scale of cold weather failure moves from anecdote to epidemic. Between 1995 and 2005, the U.S. Department of Transportation logged 861 weather-related rail incidents, 660 of them outright derailments, each one a data point in a pattern too large to ignore. These were not isolated acts of nature, but a statistical map of systemic breakdown. Regional clusters emerge along the northern corridors where sub-zero fronts settle in for weeks, and every mile of track becomes a test of mechanical endurance. Drill into the records and the same culprits appear over and over: fuel waxing below the cloud point, oil viscosity climbing past safe limits, air brake seals bleeding pressure into the wind. The department's breakdown is clinical, each entry tagged by subsystem, each failure a known quantity. Yet for a decade, these numbers sat in the database, unremarked, while the industry debated the cost of closer hotbox detector spacing and stricter additive protocols. The accidents did not cluster around freak storms or once-in-a-century lows. They followed the ordinary winter, the one everyone expected. The cold was not a surprise. The surprise was how little changed in response. This is not a story of rare disaster, but of routine risk normalized by repetition. The evidence is not in the headlines, but in the quiet, relentless accumulation of failures. Each one a warning, each one logged, each one left to repeat. Number 4. The 1918 circus train hotbox, where the chain of cold weather bearing failures first forced itself onto the national stage. On a June morning near Hammond, Indiana, a circus train, already stopped by a seized axle, became a stationary target. The bearing had overheated in the night, forcing the crew to halt on the main line. Minutes later, a troop train, its engineer asleep at the throttle, tore through the stranded cars at 35 miles per hour. The wooden coaches and kerosene lanterns did the rest. 86 lives were lost, many burned beyond recognition, in a single firestorm that began not with human error, but with the collapse of a thin film of oil between steel surfaces. The Interstate Commerce Commission's investigation named the engineer's fatigue as the proximate cause, but the root was mechanical, a hotbox that turned a routine stop into a mass casualty event. The shock of Hammond did not fade. Over the next 4 decades, hotbox derailments continued to claim lives until the 1963 sealed bearing mandate finally forced the industry to act. The rule was simple: close the system, keep the oil in, and the contaminants out. Hotbox incidents fell by 70% in the following decade. Yet the lesson lingers. Cold did not invent the weakness, it exposed it, and only regulation closed the gap. Every modern detector, every bearing threshold traces its lineage to that night in 1918, a century-old warning that the physics of oil, steel, and cold remain unchanged, even as the names and faces do not. Number 3. East Palestine, where the cold's quiet sabotage met a wall of procedural neglect. On the night of February 3, 2023, a Norfolk Southern freight train rolled through sub-zero Ohio darkness, dragging with it a bearing already in the grip of collapse. The hotbox detectors did not fail to speak. Their readings rose in a sequence that left no ambiguity. First, a warning at 38 degrees above ambient, then a spike to 103, and finally the critical alarm plus 253 flashing red across the system. The company's own rulebook demanded an immediate stop. Instead, the crew pressed on, aiming for the next siding, the bearing now running dry, its oil film long since stripped away by the cold. Within minutes, the inevitable. 38 cars derailed, 11 of them loaded with hazardous materials, vinyl chloride and propylene oxide, a chemical inventory that would haunt the landscape for months. The NTSB postmortem was blunt. Jennifer Homendi called it 100% preventable. Every safeguard existed on paper: anti-gel additives, heated fuel lines, redundant handbrake policies, and a clear alarm threshold for the detectors. Yet on the ground, only one handbrake had been set. The additive had not been dosed. The detector's critical reading had been logged but not obeyed. This was not a failure of knowledge or technology. It was a failure to act on warnings that the physics had already made urgent. The cold did its part, thickened the oil, starved the engine, and forced the bearing into thermal runaway. But the disaster belonged to the institution that saw the numbers, heard the alarms, and chose to wait. In East Palestine, the villain was not the weather, but the decision to let a known risk run unchecked until metal, pressure, and heat made the final argument. Coming to the top 3, the Kicking Horse River disaster is where physics and policy collided, leaving no one in doubt about which would yield. In the pre-dawn hours of February 4th, 2019, Canadian Pacific Train 301 sat parked on Field Hill, its air brake cylinders quietly bleeding pressure into the minus 28 degrees air. 3 hours on the grade, 3 hours for the cold to harden every rubber seal and erase the engineer's only margin against gravity. Andrew Dockrell, the conductor, had filed a hazard report just a day before. It said, "Extreme cold compromises brake performance on Field Hill." The memo reached management. It was closed without action. 6 weeks earlier, the last institutional barrier had been removed, a winter operating rule that forbade trains from descending Field Hill below minus 25. The memo that killed the rule spoke of operational flexibility and cost savings. It said nothing of the 25 prior runaways, nothing of the physics that had not changed. On that morning, Dockrell, Dylan Paradis and Daniel Waldenberger Bulmer worked through the checklist as the train idled, waiting for a relief crew. The Ogant's emergency valve, meant to dump water and buy precious friction, remained untouched. No one triggered the protocol, no one wanted to risk contaminating the brake system. The final radio call, captured by the TSB, is chilling in its clarity. He said, "I'm losing pressure. I'm pulling the brake now. I'm at -28. I can't hold it." Moments later, the train rolled, uncontrolled, into the Kicking Horse curve. 2 lives ended in the river, a third in the wreckage. The cold did not invent this tragedy. It revealed the cost of ignoring warnings, of treating human caution as an inconvenience. The Dockrell report, the repealed rule, the untriggered valve, each was a decision to trust institutional optimism over the known schedule of physics. When the cold came, it kept its appointment. The institution did not. And finally, in first place, the mathematics of institutional failure stands as the sum of every omission, every shortcut, every warning left unread. The cold, with its silent arithmetic, never varied. -28 hardens a seal, -12 gels a fuel, -10 thickens oil beyond the point of rescue. These numbers were not secrets, they were published in manuals, codified in ASTM standards, logged in the ledgers of every engineer who ever watched a bearing die in February darkness. What changed was not the physics, but the willingness to treat it as negotiable. The ledger of available mitigations is stark. Anti-gel additives, proven to lower the cold filter plug point by 20 degrees, were mandated on paper for every locomotive north of the 38th parallel. Yet in East Palestine and on Field Hill, fuel samples revealed no additive at all, absent by cost-saving design, not by accident. Heated fuel line systems required by AARS 5000 for continuous operation below -10 covered 0% of the Canadian Pacific line where the Kicking Horse disaster unfolded. The price of full detector coverage, $12 million a year, to halve the spacing and close the blind zone, was weighed against billions in damages and found excessive. Every safeguard existed, every fix was known, and everyone was deferred, diluted, or deleted in the name of operational flexibility. The Association of American Railroads produced the cost-benefit tables. The National Transportation Safety Board and the Transportation Safety Board of Canada wrote the recommendations. Notch 3 to 4 preheat, Ogant's valve deployment, handbrake redundancy, automated alarm response, all mapped, all documented, all left to the discretion of managers whose incentives ran on a different clock. The gap was not technical, but institutional. It is visible in the table of mitigations, a matrix where every cell that reads absent or incomplete is a decision, not a surprise. This is the equation that closes the list. The cold strips away the margin for error, but it does not invent the weakness. It exposes it, relentlessly, until physics makes the final decision. The disasters at East Palestine and Kicking Horse were not acts of nature, but the result of a system that allowed engineering limits to become optional. The victims, Dockrell, Paradis, Waldenberger Bulmer, and the unnamed dozens who came before, were not lost to the weather, but to the refusal to enforce the rules that the weather made necessary. The accountability map is clear. Every omitted additive, every deferred retrofit, every erased restriction is a variable in a calculation that always ends the same way. The only fix is to treat cold not as an inconvenience, but as the final authority. Until then, the schedule will remain fixed, not by the railroad, but by the laws of thermodynamics, and by the silence that follows when no one listens in time. Across all 10 disasters, one pattern endures. The cold didn't invent these failures, it revealed them. Physics set the clock, but institutions chose to ignore it. Different countries, same system. Every time, the real catastrophe began with a warning unheeded, not a temperature reading. In railroading, the only variable is whether someone listens before the cold forces its verdict. Thanks for watching. Drop your thoughts below.